All right, so we talk about construction methods like Merkle-Damgard and sponge. So historically, we will see some examples of hash functions, and almost all of them will be Merkle-Damgard constructions. Then I will talk about SHA3, which is a sponge function. So let me show you the picture of the MD4. This is one round of MD4, and it consists of 48 runs. So just repeat this process 48 many times. It was developed by Ronald Rivers in 1990. Block size is 512 bits. Just remember the Merkle-Damgard construction. We divided the message into blocks. This is the length. Okay. The message digest length is 128 bits. So here we have actually words A, B, C, D of 32 bits. So this is 128 bits. So initially you fill it with IB. Then feed the message from here, 32 bits by 32 bits by modular addition. And after 48 runs, you end up with some value here, right? Then you also XOR it with your IV and say that this is the hash output, okay? So this is why in the following picture, when the message digest length will increase, we will see that more words are added to here. So this is Merkle-Damgard construction. Basic idea, MIs, as I mentioned, are 32 bits parts of the message block. KIs are just constants. And this is left rotation by S bits, okay? So here there are modular additions, here rotation, and there's a F function here which takes 3 inputs, B, C, and D. Then perform just logical operations like XOR, and etc. I will show what it is when I talk about MD5, okay? So there's very simple operation, as you can see. This is just, you almost use no memory. This is just logical operation, so it is very fast on any software or hardware. Okay. The bad thing is that this was broken years ago in a very bad way. So generating a collision takes a few microseconds. Premise resistance is also broken. But of course, since nobody is using it, maybe agencies or cryptographers who work on this, if they have the time, can find better attacks than this. So don't rely on this. It might look like it is secure for preimage, but actually, since nobody's analyzing it for a very long time, there may be a lot better attacks. So it was a standard for a long time, but retired in 2011 with RFC 6150. As you can see, although it was broken, people kept using it for a very long time. It influenced many other designs like MD5, SHA1, SHA2, RIPE MD. So let's look at MD5. The only difference is that instead of 48 rounds, as you can see, it is 64. So, make attackers harder. And as you can see, there is another addition here. So this arrow wasn't here in the previous picture, okay? So let's talk about what this F function is all about. So it takes 3 inputs. Since it is, 64 rounds, in the first 16 rounds, this F function worked like this. Then this, and this. So as you can see, the operations are AND, OR, NOT, XOR, and that kind of logical operation. So it is really fast. Collision resistance, generating a collision requires 2 to the 18 operations, less than a second on a regular computer. Pyramid resistance is also better than an exhaustive search attack. In 2004, it was shown how to create a pair of files that share the same MD5 checksum, which is a very bad thing for cloud services. If you only keep MD5 hashes, then you can, obtain different files same hash file output for different files, which is also problematic like BitTorrent or that kind of services if you rely on MD5. In 2005, Lanstra, Wang, and Weger demonstrated construction of 2 X509 certificates with different public keys and the same MD5 hash value. 3 years later, it has shown how to fake SSL certificate validity, so certificate authorities should stop using MD5. Of course, nobody stopped using it, by the way. In 2012, the authors of Flame malware used an MD5 collision to forge a Windows code signing certificate. Okay, and Flame was one of the first malware that spread almost the whole world. Okay, so it was important. So here's an example. This is X1 is a single message of 512 bits. X2 is another input. The black parts are identical. The red parts show the difference. For instance, this is 7 here and this is F here. So if you think about bits, this is 0, 1, 1, 1, and here it is 1, 1, 1, 1, all 1. So you're flipping the most significant bit of this nibble. So as you can see, this is what we call a differential attack. You are simply changing a few bits in the input, but obtaining the same output value. So this is just an example for an MD5 collision. So what is next is SHA1, but this was developed by NSA. And initially, it was published in 1993, but 2 years later, I think they added this rotation, if I'm not mistaken, or this one, but I remember like this. So they made a modification and called this SHA1, and the previous one is called SHA0. As we can see, the message digest length is now increased from 128 bits to 160 bits. So difference is 32 bits. This is why we have the word E here compared to MD4 and MD5. Okay. The number of runs also increased to make differential attacks harder, but the rest is almost identical, as you can see. Okay. So here's an example how this works. So this can be seen as a test vector, but I also want to show how hash functions work in practice. So assume that your input message is ABC. This is very important. I'm writing these characters as an ASCII code. Okay, all of them represent a single byte. This is not hexadecimal notation. This is very important because I observed that many people who implement hash functions sometimes confuse hexadecimal with ASCII code, because, for instance, they write their code and provide hexadecimal input and obtain the output, then go to an online, for instance, SHA256 calculator and put the same hexadecimal value as input and realize that the output is not identical as their code. And they think that they made an implementation error. But the thing is that when you write an hexadecimal value as an input, actually the web page thinks that it is an ASCII character, not hexadecimal. Okay, this is very important. Some people still confuse this. So here we are actually providing 3 bytes input. Okay, so in your keyboard you press ABC. So IV is this. This is fixed in the standard, so you can go to documentation and see this. Okay. Sorry, IV is here. Sorry, my bad. This initial hash value is as follows. Sorry. Yes, IV is here. ABC is here. Sorry. So as you can see in the ASCII character, A is for 61, this is for 62, and this is for 63, and 80 is the padding. So you start with 1, then many zeros, right? Then at the end, you see 18 here. Actually, this is the length of the message in terms of bits. So since here you have 3 bytes, it's 24 bits. But if you write 24 in hexadecimal notation, this is what you see. Okay, so this is your block content. Okay, this is the message you want to take the hash. Okay. So you fill it with the IVs and perform these operations. Again, IV is fixed. It is in the documentation. After every round, this ABCDE value is modified where you are feeding your messages from here with ended at the counter and constants and so on. So after 80 rounds, you end up with this. Okay, so you write it here. You write the IV again. So if we go back, it was from here. This was the initial values of ABCDE. Then you also add it. This is not XOR. This is modular addition, like this symbol here. Okay, it is modular addition 2 to the 32. So then at the end you obtain this value, and this means that if you take the SHA1 of an input consisting of ABC, this is the output. So you can actually create a text document and just write ABC there, then calculate the hash of it, then this should be the result. And many operating systems actually have built-in functions for SHA1 and SHA2. Okay. On Windows, you can use cert util command to do this. All right, the thing is that SHA1 is not secure because the collision resistance is not 2 to the 80 as it was expected from the birthday paradox, but it is way less than this due to Wang's attack. But this was a theoretical attack for a very long time because it required a lot of memory and computational power to obtain a collision. So it was a huge debate if somebody can find a collision in a short time. So you can even find this kind of thing in gambling websites, saying that, a SHA1 collision will occur before 2020 or something like that. But SHA0 collision can be found with practically, actually. So this is why, we can understand why NSA made a modification after they introduced SHA0. And since 2017, browsers stopped accepting SHA1 SSL certificates. This is why after that date, you will see some web pages where your browser are reporting a red error saying that, your communication might not be secure and so on. So what happened to the theoretical attack? Actually, a practical collision was found in 2015, but we call this a free start collision because here, as you can see, there is IV of this IV and message and IV and message. Both of them provide the same output, but the thing is that, of course, the messages are different. Here you start with 9D, here you have 3F, but IVs are also different. For instance, here you have 90 and you have 91. This is why we call it a free start collision. So this was found by Stevens et al. Just by using 64 GPUs, where they performed 2 to the 57 SHA1 evaluations. A free start collision breaks the inner layer of SHA1, does not directly translate into a collision on the full SHA1 because the attacker is not able to choose the initial internal state, right? You cannot introduce difference. I mean, in libraries like OpenSSL, you can provide the IV yourself, but if you're communicating with somebody, you wouldn't change the IV, right? You should stick to the same IV. But here, Mark Stevens actually tried to show that they found this by using just a small number of GPUs for a few months. He said that if he had more GPUs, he would find a real collision. So in order to prove that, Google said that we have many GPUs, just use them and see if you can find it. So he teamed up with people at Google. And actually, he didn't know how many GPUs he had control over. So he just simply give the code, run it. And if there are errors, he modifies it and so on. But at the end, in 2017, they obtained a collision. Here, it is not one message block, but two message blocks. Okay. Here, the IVs are the same. So there are no longer difference in the IV. So it is no longer a free start collision, but the differences are introduced in the message blocks. And this way, you obtain the same output. The thing is that you can add previous blocks to this stuff, identical stuff, and still obtain the same hash value. So you can, add prefix to these hashes. Actually, this is used in Bitcoin SHA1 bounty to obtain the same hash because this is not directly a collision for real SHA1 because in real SHA1 the IV is fixed as I showed you in the test vector, right? So in order to use that IV and still obtain a hash collision, you have to add a few more blocks before this. Okay. So SHA1 is broken, but we end up with this SHA2. It was again developed by NSA. This time, the message digest length is increased. Recall that due to birthday paradox, this one produced 112-bit security, this provides 128-bit security, and this provides 256-bit security. So they actually allowed message digest length due to your use case. For instance, if you are using AES 128, this means that you are at the level of 128-bit security. But as the hash function in the same protocol, if you are using SHA-512, this is meaningless because this provides you 256-bit security, but at the AES level, you stick to 128-bit security. So if you're choosing your algorithms, you have to choose all of them at the same bit security, okay? So this is why SHA-256 is useful for people using 128-bit security. But if you need military-grade security, you should use this one. So number of runs actually depends on the message digest length, also the block sizes. But as you can see, there are more words now, so that it can support 256 bits. So there are more operations like majority here, sigma, and so on. But all of these functions are also defined like this, so they are not that different. But sigmas are, rotation and XORs of the input word to itself, which is also used in, by the way, ASCII-like ciphers. Okay. So they made things a lot more complicated. As you can see, there are a lot more additions and so on. So this is why currently we don't have any practical attack or any theoretical attack for SHA2. So even the collision resistance, we cannot find full collisions, but pseudo collisions to 46 rounds of SHA256, which is actually 64 rounds. Okay. And for the premise resistance, a 211 attack breaks premise resistance for 57 out of 80 rounds of SHA512. Of course, by breaks, it's again theoretical. It's just better than the brute force attack. And you can also break 52 out of 64 rounds of SHA256. So SHA2 is not broken. But the thing is that, as you can see, until here, historically, we broke everything similar to SHA2, right? So this is why we needed something more. I mean, we have another candidate for very similar to SHA1. We go back. We have RIPE MD 160, which still provides 160-bit output, but no collision was found for it. So you can use, if you want 80-bit security, but for other purposes, you should stick to SHA2. But again, since MD4, MD5, SHA1 are broken, only SHA2 remained, but it was similar to previous designs. So if somebody could break it, there would be a huge problem because we are using hash functions everywhere. This is why NSA announced a hash competition between 2007 and 2012. This was very important because the academic community learned a lot about hash functions during this competition. They received 64 submissions. 4 of them had Turkish designers. Unlike previous competitions, NIST allowed designers to tweak their algorithms after round 2, so you could do small modifications if necessary. So all of this competition, you can go to SHA3 Zoo webpage, where everything is explained, all of the candidates, all of the attacks, and so on. But to make the story short, Ketchak was the winner of this competition. It was designed by Bertoni, John Damon, Michel Peters, and Gilles van Arche. And John Damon was also the designer of AES. So he won 2 competitions. So people thought that if you add John Damon to your team, you win the competition. But recently, NIST lightweight competition ended and John Damon's team couldn't win. So don't rely on this. But again, this time it is a sponge construction. As you can see now, the things have changed. Since it is a sponge construction, it has an internal state of large state, which is this time 1600 bits. So it is represented as 3-dimensional. Think about AES, we represented it 4x4 matrix, right? Here we represented in 3 dimensions, 5 times 5 times 64 bits. So this is how you represent and perform operations on them. Block size depends on the message digest length. Number of runs also depends on it. But as you can see, these lengths are identical to SHA2. So this is because if something happens to SHA2, you should only change your algorithm. You shouldn't need to change, database design or anything because of these lengths are identical. You could simply move from SHA2 to SHA3 if necessary. So at the beginning of the competition, our aim was to have also something better than faster than SHA2, but generally SHA3 candidates wasn't as fast as SHA2 at the end. Okay. So this is why we have 2 hash functions, SHA2 and SHA3, which are both secure, but SHA3 is our backup plan. If something happens to SHA2, we can move on to SHA3. But also, it's a personal choice. For instance, in Bitcoin uses SHA2 because it was invented before the competition. But Ethereum is announced after this competition, so Ethereum uses Ketchak most of the time.